Good afternoon, everybody. Good afternoon. How are you all doing today? Good? Everybody is doing fine? So, to people who are actually listening to this recording and not turned up in the class, today I will be probably using a board much more. So the recording is not going to have it. So try to attend it tomorrow. So I will be using a lot of boards, Blackboard today. So most of it might not end up in the recording. And we will today start seeing the microarchitecture. So in general, we have seen till now how we design sequential circuits, combinational logic circuits. Last week, we saw the architecture. What is an architecture? What comprises of an architecture? If I come and ask, what is an architecture for you all? What do you answer? Like, what is an architecture? It is a set of basically instruction set and a bunch of registers which hold the architectural state, right? Today what we are going to, and we saw some instructions like R type, I type, J type. Hopefully the assembly programming part was completed last week. So we saw how these sequence of instructions are going to be executed. And today what we are going to see is how each of these instructions are actually implemented in hardware. So we'll basically see what's an overview of the MIPS microprocessor, what's the microarchitecture, how each instruction that we saw gets eventually fetched, decoded, executed, and how you get back the results, and how that consequent instruction is executed, and how all these things are done in hardware. So basically what we are going to see is the microarchitecture part. We saw all the way up. We jumped last week to the architecture, which is, as I said, a bunch of instructions that is available to the programmers to use, along with a bunch of registers which kind of hold what we call as the architectural state of the system. Today we'll cover microarchitecture, that is how each of these instructions are going to be implemented in hardware, and see the flow of the conversion from the machine code that you saw, like instructions getting converted to machine code, how this gets actually converted and decoded and implemented in hardware. This is a very fundamental step for you to understand the remainder of the course. So we will start today with single cycle architecture, and we will continue it tomorrow. And then in the next weeks, you will go forward and see what is a multi-cycle architecture, how it is implemented, what are pipelined architectures, as Professor Onur Mutlu mentioned last time, how these systems are actually implemented in hardware, because most of modern processors that you're using, most commercial processors, are pipelined. But in order to understand pipeline, you'll have to start somewhere in single cycle. So there are not many commercial high-performance single-cycle architectures today, but this is fundamental for you to, or it kind of makes it easy for you to understand the remainder of the course. So what is a single-cycle architecture? A single-cycle architecture is, as the name suggests, each instructions, you saw add, subtract, load word, store word, all these instructions. So each of these instructions will be executed in one single clock cycle. So let me quickly show you in an illustrative fashion what each of these mean. So when there is an instruction, what happens? You'll have to fetch this instruction. So you basically do an instruction fetch. After you read this instruction, what do you have to do? So you have a bunch of machine code, hexadecimal values. Yeah? You have to decode it. So you go decode the instruction. And when you decode the instruction, you will identify some registers that you need, or probably some memory, which are the operands. So let's say you have some kind of a register fetch, or some kind of a register fetch, register read write. And then after you have all the required values, what do? Execute it, right? So you need an execution unit, or depending on what the operation you have decoded, you need to execute it, or you need to perform the correct operation. And then you have to either store the result back into the register or into memory, or probably you will not do any store operation. You just go to the next instruction. So in a single cycle architecture, all these processes happen in one clock cycle. So every instruction executes in one cycle, the next cycle comes in, you have the second instruction. The bottleneck, so what this actually translates is that this actually, the slowest instruction to execute in the processor will define your clock speed. In a multi-cycle architecture, what's going to happen is that I have shown one instruction is split up into multiple steps. So each of these steps is potentially going to be executed in one cycle. So you will have the same instruction. So the instruction fetch in one cycle, decode in one cycle, execution in one cycle, and so on. So you will have this kind of a scheme, but it will take probably 2 or 3 cycles to execute a single instruction. And as we go down to pipelining, what happens here is that you have this. So this can be considered as one single pipeline. And in a pipelining architecture, you will have multiple of them. So you will have multiple instruction fetch, decode, execute pipelines, all operating parallelly. So now what you're going to do is you're now going to execute or process multiple instructions at the same time. And what this basically means is that the architecture is going to get much more complicated, because you have to solve dependencies. For example, if you're going to do an add followed by a multiplication operation, and you need the result of the previous operation for the add operation, you need to somehow check for these dependencies and do some reordering and things like that. So you will actually be seeing all these things after in the multi-cycle and pipeline architecture. So there's much more logic that has to be implemented as we go multi-cycle and pipelining. And now, this week, we will start simple single-cycle architecture. Okay? Any questions till now? So, again, we go back to I have to keep rising and. So we go back to this operation scheme. So where do we all start? So what does our microprocessor do? You fetch instructions first, right? But you have to fetch it from some location. So all these bunch of instructions is stored in a particular memory. That's the first kind of precondition that we always assume. And now what happens is we start from here. We start reading one instruction. We decode what the instruction has to do. Exactly what I mentioned. We find the operands, whether it's register or memory. I forgot to put in memory here, so you find where you have to feed in the data. And then you perform the operation if whatever is needed. So you have add, subtract, load, or whatever is the operation. You perform that corresponding operation, and you write the result again. It's if necessary. And then you go back to the next instruction. So these are the kind of steps that our microprocessor has to do in order to execute one single instruction. And a set of instructions become a program. So let's start with what all we want, right? So I'll use this part of the board for the hardware that we need. So we start with instruction fetch, right? So we need to fetch these instructions from memory. which basically means that we need let's call it instruction memory, just for simplicity. Then what do we need? You're going to decode the instruction, so we'll come to that there. So and then you need to find the operands, or fetch the operands. So you need a register file, right? We already saw this register file when we saw the architecture. How many registers does the MIPS have? 32, perfect. And how long is what is the data word size? What does each register contain? How many bits? 32 bits. So you have basically a 32-bit value, and there are 32 registers here. So you need a register file. We'll come back to this. And then what else do we need? For execution, we need an arithmetic logic unit. We need something to perform our add, subtract, and other operations. So let's say I will just draw a block here, call it arithmetic logic unit. What else do we need? Is that all? So we have a register file, we have instruction memory, we have something that probably does the operations for us. Yeah? Good. Let's say control unit. But so it generates appropriate signals, but we'll come to it. It's needed. Something is missing here. We talked about register file. What happened to the other part? If you want to have more, if you want to fetch data from some other part of, yeah.
We need buses.
No, still we're missing something. Yeah, good. Yeah, we need data memory. So we need a data memory. So typically, depending on the architecture, both instruction and data can either be in one single memory unit. Sometimes it's separate, but for easier understanding, let's simply say we have an instruction memory and a data memory that is separated, okay? So pretty much these are the main pieces of MIPS, right? And you have, let's start with memory to store program. We have a register file, an ALU to perform the operation, data memories to store more data. We will see about control unit as we go forward. We're still missing a few minor pieces. And those minor pieces are basically, you need a program counter. Do you remember the program counter? So it's basically a register, a 32-bit register. Let me try to draw it somewhere here. It's easier. So it's basically a 32-bit register which holds the address from where the next instruction has to be fetched. And this keeps increasing depending on the instruction, but typically it increases by 4. And if it's a jump instruction, then this will hold the address to which we have to jump to fetch the next instruction. And of course, we have some logic to decode the instructions. And we also need a way in which we can manipulate this program counter if we encounter a branch operation. Typically, it's what? You have one instruction, the instruction memory, as I mentioned last week. You have the memory which you jump by 4 because of the type of memory. And sometimes you don't have to simply jump by 4 because you encounter a branch operation. You have to calculate a completely different address. So you need some logic for manipulating the program counter for branches. So these are the main components or the basic components of MIPS. And what we are going to see today is how all these things are going to come together and how you are going to you will actually see how these instructions are going to be executed, implemented. And you will see all these things actually in the lab. You'll do it yourself. Starting from the arithmetic and logic unit next week till executing your own assembly level program on all the components that we are seeing. So you will have a practical experience as well on how these things come together. Good? So before we go further, each of these different components that we saw are all are going to implement some kind of state machine. Remember state machines? Last year we saw it. No, we saw it a couple of weeks ago. So, just for a quick revisit, you remember the state machine has this current state, which is actually, there's a register which holds the current state. Then you do some kind of a combinational logic to compute the next state. And you have control signals. And then you have a clock signal that at every clock signal you move from one state to the other, depending on the control signals and the data. And some of them are going to actually implement this kind of a design. So it's good to kind of revisit this and understand how this works. So let's get started, actually. So let's start with a set sequence of instructions that are stored in memory. So let's consider this to be the instruction memory. And as I mentioned last week, your memory representation is typically bottom-up. So whenever you have a reset, the program counter starts at a fixed memory address. This is fixed for different architectures. For this particular MIPS architecture, we fix it at this value. And typically, this is read-only for our educational purposes. Let's keep this read-only. But in modern architectures, it's both read and write because you load new programs as you execute. Because it's not, so for this architecture, we keep it read-only. And again, memory addresses, they are 32-bit wide. So you can typically address 4 gigabytes of data. And now we start, so as I said, we start with the most fundamental block of executing any instruction of the microarchitecture, the program counter. So let's see what we need in a program counter. So if I draw here, is everybody able to see it? So you have a PC. It's clear? The last rows, you fine? Okay. So what do we need in a program counter? What does it do? What's the output? Let's start there. What should be the output of the program counter? Yes? It's the instruction memory address. So let me call this PC underscore next address. And this is going to be a 32-bit value. What's the input? Or what's the current data? Actually, it should be the other way around. Yeah, I'll come to it. So what should be the input? Yeah. Yeah, we have reset, sure. Let's go for that. Let's say a reset. Okay. What else do we need? Yeah? A clock, brilliant. So we need a clock. What's the input? It's going to be another address, right? It's going to be this, let's say PC underscore P. I think depending on how you see it, it's going to be, so this is also going to be a 32-bit value. So these are all the things that are going to be, this is the block or the module diagram of your program counter, right? How do we implement it? Exactly. So what you have is pretty much in Verilog, this is how you implement it. Remember, you will see a very high similarity of FSMs. So you need to be, so you start with declaring a 32-bit, two 32-bit values. So it's for the present state and the next state addresses, as we saw here. And then we need a combinational logic to compute the next address. And it's simply addition by 4. So you have a simple combinational logic. This is actually wrong. Guess the problem here? There is a, which somehow I completely overlooked. Yeah? That's okay. That's okay. That's still. There is okay. There's still something. Oh, okay. Why? That's kind of a minor issue, I think. But here we have a bigger issue, if I remember correct. Yeah.
So
Exactly. It should be a blocking. No, it's the other way around. So it should be an equal. It should not be it should not have the arrow mark. Anyway, so then we go into the always block. So remember the good old always logic? We have at every rise of the clock, you need to increment your PC address. So your next state has to be your present state has to be the next state. So at every positive edge of the clock, you compute your program counter value. And whenever it is reset, you assign your default value, which you saw, the 400,000 as the value. And here you have an asynchronous reset. What's an asynchronous? Yeah, sure.
Is there a particular reason why we use the falling edge of the reset?
Good question. It's historical, more or less, because of some of the technologies that we used to use in the past. But an easier answer would be that it's much more easier to get glitches in the circuitry, which is like quick shot of voltages, which means your system is going to get reset unnecessarily. So it's much more more stabler when you look for a high level to a negative level, because this kind of a glitch is very rare. One answer to it, but there's also other answers of how these transistors were implemented in the technology and things like that. You can say that just to prevent glitching of the circuit, because you have because it's an asynchronous reset. If it was synchronous reset, it was fine, because the glitch has to happen exactly along with the rising edge of the clock. Then only the system will reset. It's much more rare. But when you're implementing an asynchronous reset, at any point when you have a glitch in the circuit, your system is going to get reset. So it's just for more stability purposes, among other reasons. So where was I? Yeah, we just talked about asynchronous reset. And so pretty much we have implemented the program counter. And so, yeah, we got one part of the architecture already done. So we have the program counter now. So let's go further, where you are going to actually start implementing each of these instructions, how they are going to be executed. So a quick recap again. You have 3 different types of instructions: R-type, I-type, and J-type. You have a question?
Yeah.
Sure.
Can you go back to so is there any specific reason why we should have the address as input and not the increment? Because like this we can't do jumps or branches.
We will come to that. This is exactly why. So this is for now, for the time being. Okay? By the time I don't know how fast I will be able to go today, but by end of this week, this for the time being will change completely. So, any other question? Just to make sure, it's simple. We start simple. I don't want to straight away put in logics. Okay, so we have 3 types of instruction, and it's always good to start very simple. So we start with a subset of MIPS instructions, like add, subtract, and some logic operations, like let's consider them R-type instructions on the whole. And then we will slowly add memory instructions and see how we have to modify our MIPS data path circuit to actually enable it to execute memory instructions, and how then after that we will further modify the circuit or the hardware to enable execution of branch instructions. For example, as your colleague said here, PC, why do we just simply increment? What happens when branch? We will see exactly that point. How to modify the program counter to actually include for branch instructions as well, and among other modifications we have to do. And then again, additionally, we will have an immediate circuit, like for example, add immediate and jump. So we will go step by step. I'll try to go as slow as possible. If I'm too slow, let me know. And if I'm fast also. Anyway, so let's start with a quick summary of the R-type, just to get you back into the same frame of mind. What's an R-type instruction? Add, subtract. They have 3 operands. So let me switch on the other board. It's easier. So you have, let's say, an add instruction. And what are the operands? You have, let's say, $S0, $S1, $S2. What does it do? S0 will equal the value in S1 plus value of S2. And these two registers are called the source registers. This is the destination registers. So let's start with this example. And if you want to convert the instruction into machine code, this instruction has the following. Are you able to see the board here, the values here? So you have an opcode, this is going to be the source registers, you have the destination registers, and you are having the shift amount, which is useful for shift instructions, and then you have function. So for an R-type instruction, your opcode is always going to be 0. And all the function, whether it's an add or subtract, is defined by the funct field. Let's move forward. So we have an add, S0, S1, S2. When you convert it into machine code, this is exactly what it is. So you have opcode 0, source, all the addresses are converted. We saw this last week. And you have this as your machine code. So this is going to be the one that is stored in the instruction memory. Okay? So, now, let's start again with what we need and what we don't need. So what we need now, so here, what do we need for implementing this instruction? We saw the program counter. Let's say it's almost done. Now what do we need for the add instruction? You need to perform the add operation, right? Yeah, I'll come to you. So, and then we have the ALU and, yeah? Okay, so what else do we need? We only finished the program counter. Let's say we need an ALU now. And we also need? Exactly. So you need instruction memory and you need a register file. So we will see now how these are going to be implemented. So let's start with the register file. Let me try to go more up. Yeah. And oh, I don't want to remove anything. Let me try. So, I'm going to replace this control unit with register file. Extremely sorry. So this is going to be your register file for now. So let's say, now what are the inputs? What are the outputs? Let's do that exercise again. What do we need? Clock. Yes or no? No clock? Why? We need a clock. What else do we need? What did I say? What is the register file? It's 32 registers. Each register having 32 bits. Right? So, what do we need? Yeah?
Some data in and data out.
Data in, some data out. Let's go specific into it. Now, you have S1 plus S2. You're going to write the result into S0. So you're going to read the value out from S1. You're going to read the value out from S2. And you're going to write the value into S0. So what we need is a special type of memory. Again, for simplicity purposes, what we're going to say is we need two data out wires, right? Yes or no? So you need two read access and one write. So let me go back to this place, and I will say data out, underscore RS, which is, underscore RS, because you're going to read your source registers. Another one will be, this will also be 32-bit, this will also be 32-bit, and you need data out underscore RT, the other source register. Right? What's going to be your input? Or what data are you going to be writing? Yeah?
The sum of those
But we haven't performed the ALU yet. You're correct. But in terms of register, RD, destination. So it's RD, exactly. So you have data in underscore RD. Right? Then, we have data now. What do we need more? Yeah? Which is, what do we call it? Register selector. It's fantastic. It's addresses to exactly specify registers, right? So you need addresses. Let me call it A. What else do you need? Is one address enough? Yeah? You need 3? Great. So you need address of RD, address of RS, and you need address of RT. Are we done? Yeah?
I don't understand why the destination register is an input and the source registers are output.
You write into the register file. So let me start there. Add S0, S1, S2. You're going to read the values in S1 and S2, which means you are going to read the values of the source register, that is RS and RT. When you read out, you're going to read from the register file. So you're going to need RS and RT as the output. And when you write back the result, you're going to feed it into the register file. So you need it as the input. Understood? Are we done? More or less. So let me, pretty much we didn't cover the 32 registers, but of course it's implicit, so we need 32 registers. Every R-type instruction has 2 for reading, 1 for writing. We need a special memory. You need 2 read ports. So we saw that we need 2 outputs, and we have 1 write port, and that's the input part. And how is the Verilog going to look like? You know that these 2 blackboards cannot be operated simultaneously? It's a problem. No, okay. Oh, really? Oh, super. So now let's see. So you learn something every day. So you have the register file. And what do we need? We need a 5-bit address. So 2 power 5, 32 different addresses. So you need 5-bit values for the addresses RS, RT, and RD as an input. And you have another 32-bit input for the write back. You have an input for write enable. We will see why it's required in the couple of slides. And you need output exactly for the source register values. And then to implement the register itself, you're going to define an array of registers. And this is how you do an array of registers. How you read this is you implement 32-bit register and 32 of them. Okay? So you have 32-bit data, 32-bit data-wide register, and you instantiate, or rather you declare 32 of them. And then, straightforward, you have, for reading the RS out, the source registers out, you simply pass the address of the address as the input, so you read directly in that array. It's very standard, very similar to C programming. And again, here you do for RT the same. And for write, you always have a clock. So this is pretty much the convention. You always have, so you call this memory as asynchronous read, synchronous write. There are, of course, synchronous read and write. Typically, you don't have asynchronous read and write. So there's different types of memories. But what memory we are going to implement is synchronous write, because the write enable will be checked at the rising edge of the clock, and the data input will be then appropriately stored into the register file. So when you do an add operation, your result is going to be stored in the data is going to be stored in the address of the destination register. Simple. So we have a register file now implemented. So we can actually check one more. Are we missing something here? We are missing something here. 32 registers, fine. Are we missing a register? Everybody loved that register last week. You had so many questions on, yeah. Perfect. So we need to add the trick for zero register. We remember you had a $0 implemented or in the instruction, and this is pretty much what you need to add. So you say, if your source or your any of these registers is 0, you simply assign the value 0 out, or you pick the correct value and read it out. So it's a ternary operator. So address is 0, read RS, or just output 0. By this, you are simply implementing this $0. That's it. Got it? Yeah.
Why don't we store the 0 line in the first register?
It's up to the, it's up to the architecture how the synthesizer will say. You can pretty much say you just store 0, but this is exactly what it will anyway result in. So in hardware, when it's all converting the Verilog into hardware, this is pretty much the architecture that you will get. So it's just how to kind of describe. And you will actually have some of these files as part of your exercise, and you might have to just implement the ALU. And then you will plug in all these register files that we saw, the memories which we will see in the future. All these things you will plug it in Verilog during your lab exercises, and you will see the whole MIPS actually working. So these are all going to be part of your lab exercises as well. So we have the register file. Now we need something that actually does the operations for you, which is the arithmetic and logic unit. It's the core of the MIPS processor. So ILU basically does a whole bunch of operations, adding sometimes multiplications as well. You have shift operations, you have logic operations, and more of these. So basically what it looks like is like it takes two inputs, typically, and you have one output, and you have an F, which is basically the function that you tell to the ALU what to operate. So the ALU has adders. It has the logical operations of AND, OR, all implemented inside. You can, if you are interested in how these adders are implemented, you can look up the Arithmetic Circuits chapter of the book. But we are not going to go into details of how it's implemented in the processor. But if you're interested, you can see how adders are implemented, different ways of implementing adders, how multipliers are implemented, shifting operation, how it's performed. So you have an entire chapter in the book on ALU only. So you have two inputs, one output, and the function to specify what is the operation. So for example, if the function is, it's basically a 3-bit wire, 3-bit input, and depending on the value, the ALU will perform the following operations. That's it. And don't get worried that, so this is how your ALU design will look like. Okay? So you will take some parts of the F and feed it into the final multiplexer. You will implement your OR gate, AND gate, and you have an adder. And so this is the ALU which has all the operations that you need. Okay? You will actually be implementing the ALU, as I said, next week in the lab. The lab manual will have exactly the details why you are kind of having this architecture, how you will implement the entire ALU in Verilog next week. So don't worry if you're not understanding this. You have much more detailed explanation in the lab, much more practical next week. Yeah, question? I guess you have a question? Okay, cool. So ALU does, in some sense, the real work in a processor. And so far, so good. We have most of the components, but we still do not have data memory. We can implement most of the R-type instructions because somehow we are assuming that you have the adders and the shifter implemented in the ALU, you can implement all R-type instructions because you have an instruction, you have the register file implemented, but we don't have the shifter. But if you want to add shifting, you know what to do. So you have to implement it in your ALU unit. So we have most of the things that we need to implement all R-type instructions. We do not have data memory. And when we come back from the break, we will go more ahead and then see how we have data memory, how to do branch implementation, and hopefully tomorrow we will finish off with an example. Let's take the break and meet in 15 minutes. So let's continue. Let's continue now. So till now, we saw some parts of the MIPS architecture. And what we don't have till now is we don't have any way to read or write from memory. We have a method in which we can read or write from the register file, but we don't have anything to read or write from memory. We don't have immediate values, operations that can be done on immediate values yet. And we also have no conditional branches, no jump instructions implemented. Let's start with the memory. So again, let's go with the same exercise where we walk through what are required for data memory. So let's start with a data memory block. First of all, what's your input? What's output? What's the output? You have to focus in this part of the board, just to be clear. What's the output? What's the input? It's pretty much like a register file, right? So you have a simple data out, which is 32-bit. So whenever I mark the line on top of an arrow, it's basically a bus. And I always write the value on top of it. It's a 32-bit bus, if in case you're wondering. And then you have data input. You need what? Address. This is also going to be 32-bit. How wide is the address bit here, address value here? We saw this. For the register file, we had 32 registers, and therefore the addresses was 5-bit. In MIPS, we saw that the data values can be 4 gigabyte, good, which means 32. And you, of course, have a clock. Is there something that I'm missing? How do we write into this data memory? What do we need? It's exactly like what we needed in the register file. So you need a write enable signal as well. So pretty much this is what we need to implement a data memory. And in Verilog, you would implement something like this. So you have 65,536 values. So how you read this? Exactly like remember the register file. So you have 32-bit values and 65,536 of them. So it's an array. And your data out is a simple access to the corresponding address, which is here it's just 16 bits, but we will come why later. So, and then you have, as we saw in the register file, you have a synchronous write. So whenever the write enable is high, you simply write the data that is in the input into the memory array. Straightforward and simple. So pretty much what I had to say. So you have up to 2 power 32 bytes that can be written. Pretty much you have, in general, you have smaller memories implemented, but it's nothing important, so don't worry about that sentence. But now, when you want to read from the memory, you need to implement load word instruction, right? And load word instruction is, so till now we saw how to implement R-type instructions, and now we are going to see how we can incorporate an I-type instruction, because load word is an I-type instruction, and also we need to calculate. So let me write down So how does a load word instruction look like? You have load word into a register, right? It's a destination register, or yeah. No, it's the other way around. So it's an RT because you have only one. I'll come to that. So you have a destination register and you have an immediate value. Remember the offset value, and then followed by a source register. Do you remember the syntax? It's pretty much what it does is you calculate the address from where you have to load the data, address of the memory from where you have to load the data into a destination destination register. So what you're going to do here is the effective address is, and as I say, okay, the previous slide, you have to calculate the address from an immediate value and a register for a load word instruction. And what we are going to do is to do this calculation of the address, we're going to use the ALU because we already have an adder implemented there. So what are the other types of I-type instructions that you know? Add immediate, for example. So let's say add immediate. How do you, what's the source, what's the destination? You have $RT, $RS, and then you have an immediate value. So in some sense, an I-type instruction has 3 operands. So you have 3 operands. 2 of them are registers. One is a 16-bit immediate value. And if you remember, when you translate the instruction into the machine code fields, you have 6-bit opcode. Unlike the R-type instruction where opcode is always 0, here the opcode actually specify what is the operation to be performed. And then you have the source, you have the 2 register operands, and then you have the immediate value. So we are now going to see what are the changes that one has to do to the register file, to the ALU, to actually incorporate the I-type instruction. Because you have registers, and you need an immediate value. And remember that the address for a load word, for example, is going to be computed is using the ALU on the immediate value and the register operand value. So we need to make some modifications to the ALU and the register file. So to do that, to make things faster, unfortunately this part is in the dark, but that's okay. So what are the changes that we need to do in the register file? So this is the register file that we talked before the break. You have the destination register input 32-bit, and you have the 3 addresses, clock, write enable, and the 2 read outputs. But in order to implement an I-type, the first thing that one has to do is your RS has to be added with the immediate values, because you're going to generate this addition to generate the next, to generate the effective address. And always you will have RS is always a read. So this is always going to be an output, no matter what happens. And so let's say that if one register is written, it is RT and not RD. What does that even mean? It's here. So if you have only one register write in an I-type instruction, you're not going to use the RD at all. So this RD is not going to be useful, and you need to that we need to incorporate some kind of a switch mechanism. And for write data in, or the input that is coming into the register file, you're going to choose it either from the memory or the ALU. Why? Why memory? Because you're going to read, for example, you're going to read from the memory in a load word instruction. So your data has to come either from the memory or the ALU. Because remember, I told that you can give a direct address also here, plus the immediate and the offset and the base address. So you can either have directly the data, the actual data coming in from this memory location, or the actual value coming in from the ALU, because you're going to store from the output of the ALUs. For example, in add immediate, this value has to be stored into this register. So the data in is going to come in from the ALU for an add immediate instruction. So you need to have this option. And not all I-type instructions write to register file. Do you know any I-type instruction that does not write to register file? Yeah? Store word. Store word doesn't write to register file, but it writes to the memory. So we need to incorporate all these kind of changes into the register file implementation. And also we need to do some changes to the ALU. Because if you're no longer going to use the ALU just to compute from the source operands, you're going to use it to actually calculate memory address as well. In this, for example, in the case of the load word instruction. And the result is also used as the address, right? So you're going to use the you're going to use the address that is effectively computed here as another address for the data memory in some cases. And also you're no longer, so if you have only one input, it's no longer RT. So if you have only one input, then you also, the input comes in from the immediate value. So you need some changes here to one of the input, which is always, so you have, in a typical sense, you have RS and RT going in here, right? So you have two source operands typically for an R-type instruction. So you have add, RD, RS, RT, and this is going to be your RD typically. This is going to be from one of the source registers. This is going to come from the other source register. But for an I-type instruction, one of the operand could potentially be an immediate value. So we need to incorporate this change also into the ALU. So these are the changes that you need to do to actually also implement the I-type instructions. And if you want to do store word operation, it's also an I-type instruction. There's not much changes to be done in the way in which you calculate the address, because it's exactly the offset plus base address. And the only difference is that in a load word instruction, you have writing back to the register file. The resulting data is written back into the register, back to the register, but in a store word, you write it to the memory location. And in order to write it back to the memory location, we need to enable the write enable of the data memory. So these are some extra changes that we will have to do to incorporate for being able to use I-type instructions. Any questions? So in some sense, what we need is the following. ALU inputs has to be modified. So you need to have either the source register value or the immediate value, which is RT or immediate value. The register file has to be modified, which is basically the write address is going to come either from RD or RT. So it's no longer just coming in from one of them. So it's going to come either from here or here. And the data also is going to come. So this data input is no longer just going to come from RD, but it's either going to come in from the ALU or the data memory out from the data memory. So you need have another option here. And again, you have to enable, you have to have the write enable of register file and the write enable of memory. So these are the kind of changes that we need to be implemented. And all of them are muxes, right? They're all simple multiplexers. You can have a control signal value that actually chooses between a register value and an immediate value, or here, whether you want to feed in the data coming in from as a result of the ALU or directly from the memory. So these are all simple control signal values that needs to be implemented. And what we can now do is we can actually go step by step and see. So these are the control signals, basically. Whatever we talked in a very abstract way is now much more specific, and these are the control signals that we require for now to actually enable I-type instructions. So let's start with register write. What's register write? It basically is a simple 1-bit signal which says, okay, do the write enable for the register. You have to write into the register file. So this one becomes the reg write. So this is directly linked to the control signal reg write. Now, the reg DST is basically to determine which destination register to write. So that is defined by the reg destination. So whether you want to write your data into register RD or RT. And also you need a control signal here to determine what is the source of your data. So whether it's coming in from a register or the immediate value. And this is ALU source. And this is the control signal that shows which to use. And memory write. So if you are going to write any value back into the memory to store word, you need write enable. And this is directly linked to the memwrite control signal. And ALU operation is basically what operation you want the ALU to perform. Add, shifting, any logical operation, and so on. So let's walk through with an example, okay? So let's consider the R-type. So if it's an R-type instruction, then you have the opcodes all 0. Are you going to write into the register file in an R-type instruction? So what's the standard form of an R-type instruction? You have 3 register operands. Consider the add instruction. It's add, you have a destination register, and 2 source registers, which means you're going to write back the result into the register file. So your reg write is 1. Similarly, since you're going to write into RD, it's 1 because it's an R-type instruction. And your ALU source is not an immediate value. It's from the register, so we can indicate it by a 0. And there is no memory write because it's an R-type again. And you don't have to do any kind of, so the data is not coming in from the memory. It's typically from the ALU. So, and then the function part of the field directly relates to what operation to perform. So this is how the control table will look like. If you want to implement your control signals, which is part of your exercise next week, a week later, you will actually implement all these signals, how they are generated. Consider an I-type instruction like load word. It's an I-type, so you have a specific opcode for the load word. And you're loading. So are you going to write into the register file? Yes or no? Load word. Are you guys following me? So how is load word actually written? So you have load word, you have a destination register. So you are going to write the value into this register, which means you are going to do a write operation on the register file. So your reg write is going to be 1. Similarly, you are going to write into, R RT and not RD because it's a load word instruction, and you don't have the third operand. So you're not going to have a destination like RD register. Instead, you're going to use RT, so it's going to be 0. And ALU source. What's the ALU source? Which one will you choose? You're going to have to choose from the immediate value as well, right? So you have to have a 1 there, and then there is no memory write because it's a load word. You're not going to write into memory, and you're going to load from the memory to the register file. So you're not going to write back an output from the ALU into the register file. So you're going to write the value, the data coming out from the memory into the register file. So you have a 1 there. And an ALU op is a simple add because of the immediate plus base address. Is it clear? Simple enough? Store word, very similar. You're not going to do a write operation into the register. Your source is still coming in from the immediate value, and you're going to do a memory write operation. So you have all these 3 values enabled. And these will actually enable you to almost implement the ITAP instructions. And this kind of forms the control unit part of the whole architecture. Of course, we still have, we are almost there. Like we have all the R-type instructions. We can do read and writing from the memory now with these control signals, but conditional branches are still missing, right? So we need some way to increment the program counter, not just by 4, but by an arbitrary address. Got it? So let's see how we could implement a branch on equal, which is a conditional branching statement. And typically what you have, so the opcode for branch on equal is 00010. And what it does, the branch on equal, if you remember, is you compare 2 register values. And if they are same, you form a branch target address, which the PC has to be updated with, right? And the branch target address is basically you need an immediate value which is added to the next instruction. You will understand it better when I go further. So now, in order to actually do the comparison, we need the ALU. Because if you want to say if RS equal to RT, you need to subtract RS and RT. And then we need a 0 flag to actually say whether RS is equal to RT. And so we need to make all these changes introduce all these changes into the architecture in order to be able to implement branch on equal. And we also need a second adder. Why? Because what is branch on equal? Branch on equal has 2 registers and a destination address, which is typically an immediate value. So you need to be able to add the immediate value to the program counter. And there is one catch here. The jump address, or the branch on equal address is typically 16 bits. Right? No? I think I'm confusing you guys, but still. So let's go back now for this PC plus 4. Now let's go back to the program counter, which we haven't touched at all. We have the only thing that PC can do is you increment the PC on every clock cycle by 4. But now your PC not only has to have PC plus 4, but also it can either be PC plus 4 or the new branch target address. So you need some way to actually multiplex the PC addresses as well. And for which we will actually add a new control signal, which is called branch, which will just indicate whether you're going to have a jump instruction or not, or some kind of a branching or not. And for example, when you want to implement branch on equal, you have an opcode. And are we going to do any kind of writing into the register? No. So it's 0. We don't care about the destination address. The ALU source is an immediate value. No, it's from the register value here. And then you have the branch is enabled. You don't have any kind of memory write. And you perform a subtraction instruction. Because you have to be able to compare the RS with RT, which means you have to do RS minus RT. So you have to do a subtraction instruction, which will rise the 0 flag, which you can read and then take the appropriate branch. So we're kind of almost there. We now also have some kind of, with the branch control signal, we also have conditional branches that you can implement. But still, we do not have absolute jumps, which is unconditional. The opcode looks something like this. You have jump, and then you have a 26-bit address. So you have, it's an extremely simple machine code. So what we have here is the jump, what I indicate here is the jump target address. You remember 400,000 is the reset PC value. And then assume that, for example, you have a jump target address of this particular value. But then what you need, what you can have here is a 26-bit value. So you basically split this jump target address, which is 32 bits, and pick only the 26 bits, which is you don't care about the 4 MSBs, and you don't care about the last 2 significant bits. And this 26 bits is what will go into your jump address when you compile and when you write into your instruction. So you will have this address in the instructions machine code. So a machine code will look something like this. It will not have this address, but it will have this particular value. Why? Because it makes things much more simpler. You will not need any ALU for computing the effective address for a jump instruction. Because your jump instruction is typically only you have only this 26 bits, and you can simply use concatenations, and you don't need any kind of arithmetic output. For example, the first 4 bits is straight away from the program counter. And then, so the first 4 bits are coming from the program counter value. And then the next value, the next 26 values come from the jump address itself. So you have address, and then the last 2 bits are 0. So you can directly assemble the jump target address without the need of doing any operation. So you save time also there. And you also don't need any memory, no register file, nothing. And the only thing that we have to do is make the following change for the program counter, because now it not only has to be able to increment by 4, but also it should be able to decide whether it's just a 4 increment or it's a new jump target address, for which we add another control signal. So you add another control signal, which we call the jump. And whenever you have the instruction, the jump instruction, you pretty much don't care about anything except the jump value. And whenever this jump value is on, you appropriately switch in the program counter whether you want to calculate your address based on the target address, or you simply increment the program counter. That's it. So you basically now have pretty much, you can actually do pretty much all the operations that are required on MIPS. So we can implement R, I, J type instruction. We can calculate, we can actually do branching. In general, we should be able to run most programs. Of course, we didn't talk about quite a lot of things like multiplication, shift operation, but then you know how you can implement shift operation into the ALU. So you simply add this functionality into the ALU. And you have, so you actually implemented only LW and load word and store word. We haven't yet looked into how to implement this jump and link and jump register functions, but these things you can learn it. So it's where you can follow the same methodology and try to implement it. But for now, to kind of understand this entire flow, I think this is pretty much what you need to implement most programs. And pretty much we are done here. And when we come back next week, tomorrow, what I will do is I will use a set of slides that will actually walk you through the 2 hours of lecture that we do in a much more graphical way. So we'll use an example and then actually put all these different blocks that I was talking about individually in one particular slide and walk you through every step that we talked about, right from the instruction fetch, then followed by decode, when a program counter is incremented by 4, when it is not incremented by 4 and calculates a jump target. So you will actually graphically see tomorrow when we come, because I don't want to do it now and repeat it tomorrow. We will see how all these things actually come together, and we will finish tomorrow the single cycle architecture. Thank you very much.